Right now, tonight, one of the most familiar stars in the sky could be dying, and we would have absolutely no way of knowing. Betelgeuse, the bright reddish star on Orion's shoulder, is a massive aging giant racing toward a catastrophe that nothing can prevent. Deep inside its core, the laws of physics are pushing it toward an irreversible collapse. And here's what makes this truly unsettling. The collapse could have already begun. The core could be falling in on itself at this very moment, and the surface of the star would look completely normal. No warning, no visible change, just a calm, familiar glow in the night sky, hiding one of the most violent events the universe can produce. What happens when that core finally gives way would be unlike anything humanity has ever witnessed. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've probably seen hundreds of times without really thinking about it. The constellation Orion. If you've ever looked up at the winter sky in the northern hemisphere, or the summer sky if you live south of the equator, you've seen it. 3 bright stars in a short diagonal line forming the belt. 2 stars above them marking the shoulders. 2 stars below marking the knees. Orion is one of the easiest constellations to find. Ancient Egyptians associate it with Osiris, the god of the afterlife. The Greeks saw a mighty hunter striding across the heavens. Cultures on every continent told stories about those stars for thousands of years before anyone understood what they actually were. But tonight, we're going to focus on one star in that constellation. The one marking Orion's left shoulder, the one with a distinct reddish-orange glow that sets it apart from almost every other bright star in the sky. That star is Betelgeuse, and Betelgeuse is not what it appears to be. When you look at Betelgeuse on a clear night, it seems like just another bright star. It's one of the 10 brightest stars visible from most of the populated world. It flickers slightly, shifting between a warm amber and a deeper red, but so do many stars when you watch them through the turbulence of Earth's atmosphere. It looks permanent. It looks stable. It looks like something that has always been there and always will be. And that impression is completely wrong. Betelgeuse is dying, not in the slow, quiet way that most stars die. Not over billions of years of gradual fading. Betelgeuse is approaching the most violent possible end a star can experience. It is a ticking clock, and the alarm could go off at any point within the next 100,000 years or so. That might sound like a long time, but in astronomical terms it is the blink of an eye. The universe is 13.8 billion years old. 100,000 years is nothing. It's a single heartbeat in the lifespan of the cosmos. To understand why Betelgeuse is in this situation, you first need to understand what kind of star it is. Because Betelgeuse is not like our Sun. It is not even remotely similar. Our Sun is what astronomers call a main sequence star, specifically a G-type yellow dwarf. It's a stable, middle-aged star about 4.6 billion years old, steadily converting hydrogen into helium in its core through nuclear fusion. This process has been going on for billions of years, and will continue for roughly another 5 billion years. The Sun is in no hurry. It burns its fuel slowly and carefully. It's the cosmic equivalent of a long-distance runner pacing itself across an ultramarathon. Betelgeuse is the opposite. It's a sprinter who started the race at full speed and is now staggering toward the finish line, having burned through almost everything it had. Betelgeuse is what astronomers classify as a red supergiant. That term, red supergiant, tells you two critical things about the star. The word red tells you about its surface temperature. Betelgeuse's outer layers are relatively cool compared to other stars, with a surface temperature of roughly 3,200 to 3,400 degrees Celsius. That might sound extremely hot by everyday standards, and it is, but for a star, it is actually quite cool. Our sun's surface temperature is about 5,500 degrees Celsius. Many stars burn far hotter than that. Blue giant stars can have surface temperatures exceeding 30,000 degrees. So at 3,000 odd degrees, Betelgeuse is actually one of the coolest stars you can see with your naked eye. This low temperature is what gives it that distinctive reddish color. Hotter stars appear blue or white. Cooler stars appear orange or red. Betelgeuse glows red because its surface is relatively cool. But the word supergiant is where things get extraordinary. Betelgeuse is enormous. Not just big, not just large. It is one of the largest stars visible to the human eye, and its size is genuinely difficult to comprehend. Estimates of Betelgeuse's radius vary because the star itself doesn't have a hard, well-defined edge. It's not a solid object with a clear boundary. It's a ball of plasma, and its outer layers are diffuse and variable. The star actually pulses, expanding and contracting over cycles of roughly 400 days and longer secondary cycles that span years. But the best current estimates place Betelgeuse's radius at somewhere around 700 to over 1,000 times the radius of our Sun. Let's use a round number to make this tangible. If Betelgeuse's radius is roughly 800 times the Sun's radius, then its diameter is about 1,600 times the Sun's diameter. Now think about what that means. Our Sun has a diameter of about 864,000 miles. Betelgeuse's diameter, at that estimate, would be roughly 1.4 billion miles. If you placed Betelgeuse exactly where our Sun is right now, with its center at the center of the solar system, its surface would extend outward past the orbit of Mercury, past the orbit of Venus, past the orbit of Earth, past the orbit of Mars. Depending on which size estimate you use and where Betelgeuse is in its pulsation cycle, its surface might even approach the orbit of Jupiter. Everything inside that radius, every planet that makes up the inner solar system, would be inside the star. Earth, with all its oceans and continents and cities and people, would be engulfed, not close to the surface, not near the edge, deep inside the star, surrounded by superheated plasma thousands of degrees hot. Let me try to make this even more concrete because numbers this large tend to lose their meaning. Light, which travels at about 300,000 kilometers per second, takes approximately 8 minutes and 20 seconds to travel from the Sun to Earth. If you replace the Sun with Betelgeuse, light would take more than half an hour just to travel from the center of the star to its surface. That's how big this thing is. A beam of light moving at the fastest speed possible in the universe would need over 30 minutes to cross from the core to the edge. Compare that to the roughly 2.3 seconds it takes light to cross the Sun's radius. You could fit millions upon millions of our suns inside Betelgeuse. The volume is so immense that numbers stop being useful for understanding it. You simply have to accept that this star is vastly, overwhelmingly, almost absurdly huge. But here's something important. Size and mass are not the same thing, and this distinction matters enormously for understanding what happens to Betelgeuse Even though Betelgeuse is physically gigantic, it's not nearly as massive as its size might suggest. Its mass is estimated at roughly 15 to 20 times the mass of the Sun. This number carries genuine uncertainty. Pinning down the exact mass of a distant star is one of the hardest measurements in astronomy. We can't put Betelgeuse on a scale. We have to infer its mass from things like its luminosity, its temperature, its position in theoretical models of stellar evolution, and observations of how it interacts with its environment. Different methods give somewhat different answers, but the range of about 15 to 20 solar masses is what most current models and observations support. So you've got a star that is roughly 800 or more times wider than the Sun, but only 15 to 20 times heavier. That means the average density of Betelgeuse is extraordinarily low. Think about it. You're taking a moderate amount of mass, only about 15 to 20 suns worth, and spreading it out across a volume that could swallow the orbits of the inner planets. The result is a star with an average density far lower than the air you're breathing right now. Some of Betelgeuse's outer layers are closer to a laboratory vacuum than to anything you'd normally call a substance. The star is like a vast, tenuous cloud of glowing gas with a small, incredibly hot, incredibly dense core hidden deep inside. The surface that you see when you look at Betelgeuse on a winter night is the outermost layer of this cloud, the photosphere, a thin shell of plasma that happens to emit the light that reaches your eyes. But the real action is happening far below that surface, in a core you cannot see, in a region no telescope on Earth or in space can observe directly. That last point is critical, and it's something most people don't realize. We cannot see inside Betelgeuse. We cannot directly measure what fuel its core is burning right now. We cannot tell from the outside whether the core is fusing helium, carbon, neon, oxygen, or silicon. We know from theoretical models of stellar evolution what sequence the core should follow, and we know roughly how long each stage lasts. But we cannot point a telescope at Betelgeuse and say, with certainty, this is exactly what the core is doing at this moment. The surface of the star, that vast photosphere hundreds of times wider than the Sun, acts like a thick curtain hiding everything that matters. Light from the core takes an extraordinarily long time to work its way outward through all that material, being absorbed and re-emitted countless times along the way. By the time energy from the core reaches the surface, all the specific information about what reactions produced it has been thoroughly scrambled. The surface tells us the star is big, it's red, it's luminous, and it's cool. But it tells us almost nothing about the time bomb ticking away in the center. Let me tell you how Betelgeuse got into this situation, because it wasn't always a giant. No star is born as a red supergiant. They become one. And the story of how that happens is really the story of how massive stars live and die. Betelgeuse was born roughly 8 to 10 million years ago. That's our best estimate, and it means Betelgeuse is incredibly young by stellar standards. Our Sun is about 4.6 billion years old. The universe itself is 13.8 billion years old. Betelgeuse has existed for less than 1,000th of the Sun's current age. It is, in cosmic terms, a newborn, and yet it's already approaching the end of its life. This seems paradoxical until you understand one of the most important principles in stellar physics. The more massive a star is, the shorter its life. This is counterintuitive. You might think a bigger star has more fuel, so it should last longer. And it is true that a more massive star has more hydrogen to burn. Betelgeuse started with roughly 15 to 20 times more hydrogen fuel than the Sun. But here's the catch. A more massive star doesn't just burn fuel a little faster, it burns fuel enormously faster. The rate at which a star consumes its nuclear fuel depends very steeply on its mass. A star that is twice as heavy as the Sun doesn't just burn fuel twice as fast. It burns fuel roughly 10 times as fast, or even more. The relationship is not linear, it's exponential. The more massive you are, the more crushingly intense the gravitational pressure at your core, and the hotter and denser the core becomes, and the faster the nuclear reactions run. Our Sun burns hydrogen at a relatively gentle rate. It converts about 600 million tons of hydrogen into helium every single second, which sounds like a lot, but it has so much hydrogen that this process can continue for about 10 billion years total. Betelgeuse, with its vastly greater core pressure and temperature, tore through its hydrogen supply in just a few million years. Where the Sun takes 10 billion years, Betelgeuse took maybe 8 million. It burned through its main fuel supply in less than 1,000th of the time because the furnace in its core was so much more intense. When a star exhausts the hydrogen in its core, things change dramatically. The core, which was being supported against gravitational collapse by the outward pressure of nuclear fusion, starts to contract. As it contracts, it heats up, and when it gets hot enough, a new round of fusion begins, burning a heavier element. For a star like Betelgeuse, the first fuel after hydrogen is helium. The core begins fusing helium into carbon and oxygen. This generates energy and temporarily stabilizes the star, but at a cost. The core is hotter and denser than before, and the star's outer layers respond by expanding enormously. This is what turns a massive main sequence star into a red supergiant. The core gets smaller and hotter. The outer layers get bigger and cooler. And the star balloons to the incredible size we see today. Betelgeuse has already gone through this transition. It left the main sequence and became a red supergiant. The hydrogen in its core is gone. It is now burning heavier elements in its core, probably helium or possibly something even heavier. But here's where the uncertainty comes in. We don't know exactly which fuel the core is burning right now because, as I explained, we can't see the core. Theoretical models can tell us the sequence of fuels and roughly how long each stage lasts, but they can't tell us precisely where Betelgeuse is in that sequence at this exact moment. We know it's past hydrogen. We're confident about that based on the star's observed properties. But whether the core is currently fusing helium or has already moved on to carbon or something beyond, that is genuinely uncertain. And that uncertainty is important because it directly affects how much time Betelgeuse has left. This brings us to something you might have heard about, the Great Dimming. In late 2019 and early 2020, Betelgeuse did something that grabbed headlines around the world. It faded, dramatically. Its brightness dropped by roughly a factor of 3 over the course of a few weeks. For a star that's normally one of the brightest in the sky, this was stunning. Betelgeuse went from being unmissable to being noticeably dimmer than usual, even to casual observers. Naturally, people got excited. Social media lit it up with speculation. Was Betelgeuse about to explode? Was this the beginning of the supernova? Were we about to witness the most spectacular astronomical event in recorded human history? The answer was no. The Great Dimming was not the start of a supernova. It had nothing to do with what was happening in the core. What actually happened was far less dramatic but scientifically fascinating. Observations from multiple telescopes, including the Hubble Space Telescope, revealed that a large convective cell on Betelgeuse's surface had ejected a massive plume of hot gas outward into space. As this gas moved away from the star and cooled, it condensed into a cloud of microscopic dust particles. This dust cloud drifted into the line of sight between Betelgeuse and Earth, partially blocking the star's light. At the same time, the surface region where the gas had been ejected cooled significantly, dimming that section of the star's photosphere. The combination of the dust cloud blocking light from the outside and the cooler surface patch emitting less light from the star itself created the dramatic dimming that the world observed. This kind of event, a surface mass ejection followed by dust formation, is actually something that red supergiants do regularly. Betelgeuse is constantly losing mass from its surface. The star's outer layers are so loosely bound by gravity that material regularly streams away into space. Over its lifetime, Betelgeuse has probably lost several solar masses worth of material through this steady, stellar wind and through occasional larger ejections like the one that caused the Great Dimming. This lost material forms a complex environment around the star, shells and arcs of gas and dust that extend outward for enormous distances. This surrounding material will become very important later in our story, when the supernova shockwave finally reaches it. But for now, the key point is this. The Great Dimming was a surface event. It was caused by activity in Betelgeuse's outer layers, not by changes in its core. The core, deep inside, was completely unaffected by what happened at the surface. A dust cloud a few 100 million miles from the star's photosphere has no connection whatsoever to nuclear reactions happening in a core that is buried beneath hundreds of solar radii of plasma. This highlights something crucial about Betelgeuse and about red supergiants in general. The surface and the core are, for all practical purposes, living in different worlds. The core is a tiny, incredibly dense, incredibly hot region where nuclear physics determines the star's fate. The surface is a vast, cool, tenuous atmosphere where convection and wind and dust determine what we see from Earth. The surface can do dramatic things. It can dim, brighten, eject material, pulsate, all without the core being affected. And the core can undergo dramatic changes, shifting from one fuel to the next, heating up, contracting, building toward catastrophe, all without the surface showing any obvious sign. This is the fundamental disconnect that makes Betelgeuse so fascinating and so unsettling. The surface is a mask. It hides the truth. And the truth is that something extraordinary is building inside this star. Something that no force in the universe can prevent. Betelgeuse will explode. That is not speculation. It is not a possibility among many. It is a certainty. Every star of this mass, every red supergiant that has ever existed in the history of the universe, reaches the same endpoint. The physics is unavoidable. The only question is when. Now, when people hear that Betelgeuse will explode, they sometimes imagine it happening tomorrow or next week. And it could. There is nothing in our observations that rules out an imminent explosion. But there is also nothing that suggests one is imminent. The honest answer is that Betelgeuse could explode tonight, or it could explode 100,000 years from now. We simply do not have the ability to narrow it down further than that because we cannot see the core. If the core is still fusing helium, then the star has thousands of years or more remaining. If the core has already progressed to the later stages of fusion, the timeline could be much shorter. And if by some extraordinary coincidence the core has already reached the final stage, the star could have days or even hours left. We have no way to tell from the outside. None. This uncertainty is not a failure of science. It's a fundamental limitation imposed by physics. The core is hidden. The surface is deceptive. The only messenger that could tell us what the core is doing, the only particle that can escape from the interior of the star quickly enough to carry current information, is the neutrino. And neutrinos from Betelgeuse's normal fusion processes are far too few and far too low in energy for our current detectors to pick up at this distance. There will come a moment, a very specific moment, when the core finally reaches its breaking point, when neutrinos will flood outward in numbers so vast that our detectors will absolutely register them. But that moment is the moment of collapse itself. It's not a warning months in advance. It's a warning hours in advance at best. When those neutrinos arrive at Earth, the star's core will have already fallen. Let me put Betelgeuse's distance into perspective because it matters for understanding both what we can observe and what the eventual supernova will look like. Betelgeuse is roughly 550 to 700 light-years from Earth. This distance, like so many of Betelgeuse's properties, carries genuine uncertainty. Measuring the distance to a star this large and this variable is surprisingly difficult. Its angular size on the sky changes as it pulsates. Its brightness varies. Dust in the surrounding space complicates observations. Different measurement techniques have given somewhat different answers over the years, but the current best estimates place it in that range of roughly 550 to 700 light-years. That means the light you see when you look at Betelgeuse tonight left the star 550 to 700 years ago. You're not seeing Betelgeuse as it is right now. You're seeing it as it was during the Middle Ages or the early Renaissance. When that light began its journey toward your eyes, the Ottoman Empire was on the rise, the printing press was only just being invented, and Columbus had not yet sailed west. Everything that has happened since then, every war, every revolution, every scientific discovery, all of it occurred while that light was traveling through space. The Betelgeuse you see tonight is a historical artifact, a snapshot of a star as it existed centuries ago. This also means that if Betelgeuse's core collapsed 300 years ago, we wouldn't know yet. The neutrinos and the light from that event would still be traveling toward us, crossing the vast emptiness between that star and our planet. The explosion could have already happened, and the sky would still show a calm, steady, reddish glow exactly where Betelgeuse has always been. We would have no indication whatsoever that anything had changed until those messengers finally arrived. The star could already be gone, replaced by a rapidly expanding cloud of debris and a compact remnant, and we would still be looking at its ghost, an image of a star that no longer exists, painted on our sky by ancient light that hasn't finished its journey. That thought that the catastrophe could already be underway and the evidence simply hasn't reached us yet captures something deep about the nature of the universe. We never see things as they are, we see things as they were. And for a star like Betelgeuse, the gap between what we see and what is real could be the difference between a living star and a dead one. So let's take stock of where we are. Betelgeuse is a red supergiant, one of the largest stars visible to the naked eye, roughly 800 or more times wider than our Sun, but only 15 to 20 times more massive. It's young, only about 8 to 10 million years old, but is already approaching the end of its life because massive stars burn through their fuel at a ferocious rate. It has left the main sequence and its core is fusing elements heavier than hydrogen, though we cannot determine exactly which element is working on right now. Its surface is a vast, restless, turbulent atmosphere that regularly ejects material into space, creating a complex environment of gas and dust around the star. The great dimming of 2019 to 2020 was caused by a surface mass ejection and dust cloud, not by any change in the core. And the star is located roughly 550 to 700 light years from Earth, close enough that its eventual supernova will be a spectacular sight, but far enough that the exact state of its core remains hidden from us. What we see tonight when we look at Orion is a star that appears calm, stable, and permanent. But beneath that serene exterior, something extraordinary is happening. The core is evolving, fuel is being consumed, pressures and temperatures are climbing, and at some point, perhaps thousands of years from now, or perhaps much sooner, the core will reach a threshold beyond which there is no return. It will begin to build something that cannot support its own weight. And when that structure finally gives way, in a collapse that takes less than a single second, the result will be one of the most powerful events in the known universe. To understand what happens in that moment, we first need to follow the core through the remaining stages of its life. Because the story of how Betelgeuse reaches its breaking point is not simple. It's not a single event. It's a cascade, a sequence of increasingly desperate attempts by the star to hold itself up against the relentless pull of its own gravity. Each attempt works for a while, then fails. Each failure leads to a new attempt using a heavier fuel at a higher temperature and pressure. And each new stage is shorter than the last. The clock doesn't just tick, it accelerates. To understand what is happening inside Betelgeuse right now, you have to stop thinking about the star as a single object and start thinking about it as two completely different things layered on top of each other. On the outside, there is the vast, cool, glowing atmosphere, the photosphere and the extended envelope, stretching hundreds of times wider than our sun and visible from Earth as that familiar reddish point of light in Orion. On the inside, buried beneath all that plasma, there is a core, and that core is a world unto itself. It is tiny compared to the rest of the star, a region no larger than Earth or possibly even smaller, yet it contains a significant fraction of the star's total mass compressed to densities and temperatures that make the surface look like empty space by comparison. The core is where the star's fate is decided, not at the surface, not in the outer layers, in the core. And the core is in a race it has been losing for millions of years, a race that is accelerating, and a race that can only end one way. When Betelgeuse first formed roughly 8 to 10 million years ago, its core was doing exactly what our sun's core is doing right now. It was fusing hydrogen into helium. This is the simplest and most efficient form of nuclear fusion, the process that powers nearly every star you can see in the night sky. 4 hydrogen nuclei, which are simply individual protons, are combined through a series of intermediate steps to produce one helium nucleus, which contains 2 protons and 2 neutrons. In the process, a small amount of mass is converted into energy according to Einstein's famous relationship between mass and energy. This energy is what makes stars shine. It's what heats their cores. And most importantly, it's what generates the outward pressure that holds the star up against the crushing inward pull of its own gravity. Think of it as a balance. Gravity wants to collapse the star. Fusion pushes outward. As long as the two are in equilibrium, the star remains stable. It's a tug of war that has been going on inside every star in the universe for as long as stars have existed. Our sun has been maintaining this balance for 4.6 billion years and will continue for roughly another 5 billion. But Betelgeuse, being so much more massive, burned through its hydrogen in a tiny fraction of that time. The furnace in its core was so intense, the pressure so extreme, that the hydrogen was consumed in roughly 8 to 10 million years. And when the hydrogen ran out, the balance broke. Without hydrogen fusion generating outward pressure, there was nothing to resist gravity in the core. So the core began to contract. As it contracted, it got denser and hotter, dramatically hotter. And when the temperature in the core reached roughly 100 to 200 million degrees, something new happened. Helium, the ash left behind by hydrogen fusion, became the fuel. Helium fusion is a remarkable process, and it works nothing like hydrogen fusion. Fusing helium is much harder because helium nuclei carry a stronger positive electric charge than hydrogen nuclei, and like charges repel each other. You need far greater temperatures and pressures to force helium nuclei close enough together for the strong nuclear force to grab them. The specific process is called the triple alpha reaction, and it happens in 2 steps. First, 2 helium-4 nuclei collide and briefly form beryllium-8. Beryllium-8 is fantastically unstable. It exists for only about 1/10 of a femtosecond, a timescale so short it makes the blink of an eye seem like a geological era. In that unimaginably brief window, a 3rd helium-4 nucleus must collide with the beryllium-8 before it falls apart. If it does, the result is carbon-12, one of the most important elements in the universe, the element that forms the backbone of every organic molecule, the element that you are largely made of. It was forged in the cores of stars exactly like Betelgeuse, through exactly this process. Some of that freshly made carbon-12 then captures another helium-4 nucleus to produce oxygen-16. So helium burning produces 2 things, carbon and oxygen. These are the new ashes. They accumulate in the center of the core while helium continues to burn in a shell around them. The star has survived the crisis. Fusion is happening again, outward pressure is being generated, gravity is being held at bay, but there is a cost, and this cost is the key to everything that follows. Helium fusion produces less energy per reaction than hydrogen fusion did. Significantly less. Each time you fuse heavier elements, you get a smaller return on your investment. The star is still generating energy, still holding itself up, but it's getting less bang for its buck. And because it's getting less energy from each reaction, it has to burn fuel faster to produce the same amount of outward pressure. The core gets hotter, the reactions run faster, and the fuel gets consumed more quickly. Hydrogen burning in Betelgeuse lasted roughly 8 to 10 million years. Helium burning lasts far less. For a star of Betelgeuse's mass, helium burning sustains the core for roughly 1 million years. That sounds like a long time by human standards. But compare it to the hydrogen phase. The star went from tens of millions of years of stable burning to about 1 million. It lost 90% of its remaining time in a single step. And the pattern only gets worse from here. When the helium in the core is exhausted, the same crisis repeats. The core contracts again. Temperatures and densities climb to even more extreme levels. And when the temperature reaches roughly 500 million to 800 million degrees Celsius, carbon ignites. Carbon fusion is a messy, complicated process compared to the relatively clean reactions that came before. When two carbon-12 nuclei collide at these extreme temperatures, they don't produce just one product. The collision can create several different outcomes depending on exactly how the nuclei interact. Some collisions produce sodium and a proton, others produce neon and a helium nucleus, others produce magnesium and a neutron, others produce oxygen and two helium nuclei. The core becomes a chaotic soup of reactions, with multiple products being created simultaneously. The ashes from carbon burning include neon, magnesium, sodium, and additional oxygen, along with free protons, neutrons, and helium nuclei that participate in further reactions. The energy yield from carbon fusion is even lower than from helium. The star is working harder for less reward, and the timescale shrinks dramatically. Where helium burning lasted roughly 1 million years, carbon burning sustains the core for only about 1,000 years. Let that sink in. The star went from millions of years to 1 million years to 1,000 years. The countdown is accelerating and it shows no sign of slowing down. After carbon burning, the core contracts again, heats up again, and reaches temperatures of roughly 1.2 billion degrees Celsius. At this point, something unusual happens. Rather than two nuclei colliding and fusing the way hydrogen, helium, and carbon did, the next fuel is consumed through a different mechanism. The intense radiation field inside the core, the flood of ultra-high energy photons bouncing around in the superheated plasma, becomes energetic enough to start breaking nuclei apart. Neon-20, one of the products of carbon burning, is partially disintegrated by this intense radiation. The photons literally smash neon nuclei apart, knocking helium nuclei free. Those freed helium nuclei are then captured by other neon nuclei, building them up into magnesium. The net effect is that neon is converted into oxygen and magnesium, releasing a small amount of energy in the process. Neon burning is even less efficient than carbon burning. The energy yield per reaction is smaller. The star has to burn even faster to maintain pressure, and the timescale collapses further. Neon burning lasts only about a year, maybe several months, maybe slightly longer. The exact duration depends on the star's mass and the details of the models, but the order of magnitude is clear. We've gone from millions of years to 1,000 years to roughly 1 year. The acceleration is relentless. When neon is exhausted, the core contracts and heats up once more. At temperatures approaching 1.5 to 2 billion degrees, oxygen ignites. Oxygen-16 nuclei collide and fuse to produce silicon-28, sulfur, phosphorus, and a mix of other intermediate mass elements. This stage is even less productive than the ones before it. The energy released per reaction is a fraction of what hydrogen fusion provided. The core is now burning through fuel at an extraordinary rate, consuming in months what earlier stages consumed over millennia. Oxygen burning lasts roughly 6 months to a year. Perhaps slightly longer for some stellar models, perhaps slightly shorter for others. But the order of magnitude is consistent. The star has gone from millions of years of hydrogen burning to roughly half a year of oxygen burning. Each stage strips away another order of magnitude from the time the star has remaining. And then comes the final stage, the last fuel the star will ever burn: silicon. When the temperature in the core reaches approximately 3 billion degrees Celsius, silicon begins to be consumed, but silicon burning does not work the way the earlier stages did. At these extraordinary temperatures, The radiation field inside the core is so intense that it doesn't just break apart occasional nuclei as it did during neon burning. It breaks apart everything. Silicon nuclei and all the other intermediate elements in the core are continuously being shattered and reassembled by the flood of ultra-high energy photons. Nuclei are smashed into individual protons, neutrons, and helium nuclei, which then recombine in different configurations. This is not a clean fusion reaction. It's a churning, chaotic nuclear storm where matter is simultaneously being torn apart and rebuilt. The process is called nuclear statistical equilibrium because the reactions happen so fast in both directions that the mixture of elements in the core is determined by statistical physics rather than by individual reactions. And when the statistics are worked out, when you calculate which configuration of protons and neutrons is the most stable at these temperatures and densities, the answer is iron. Specifically, the process primarily produces nickel-56, which is unstable and rapidly decays into iron-56. Iron is the most tightly bound nucleus in nature. It sits at the very peak of the nuclear binding energy curve. This means that iron is the most stable possible arrangement of protons and neutrons. Every other element in the universe has less binding energy per nucleon than iron, meaning every other element could, in principle, release energy by moving toward iron, either by fusing lighter elements together or by splitting heavier elements apart. And this is why iron is the end of the road. This is the reason the star's life is about to end. Every previous fuel, hydrogen, helium, carbon, neon, oxygen, silicon, released energy when it was burned. That energy is what generated the outward pressure holding the star up against gravity. But iron cannot release energy through fusion. Fusing iron into anything heavier would not produce energy. It would consume energy. It would absorb energy. The reaction would be endothermic, not exothermic. Instead of pushing outward against gravity, fusing iron would actually steal energy from the core, reducing the pressure, making the star's situation worse rather than better. This is a dead end in the most absolute sense imaginable. The star has been surviving for millions of years by finding new fuels, falling back to the next element, igniting it, and buying more time. But iron is the last stop. There is no next fuel. There is no fallback option. When silicon burning fills the core with iron, the star has exhausted its last trick. Fusion cannot save it anymore. Silicon burning, the final stage, lasts roughly 1 to 2 days. 1 to 2 days. Consider the full trajectory. Hydrogen burning lasted roughly 8 to 10 million years. Helium burning lasted roughly 1 million years. Carbon burning lasted about 1,000 years. Neon burning lasted about a year. Oxygen burning lasted roughly 6 months to a year. And silicon burning lasts about a day. The acceleration is staggering. Each stage is not just shorter than the last. It is dramatically, exponentially shorter. The star spent millions of years on its first fuel and less than 48 hours on its last. During all of this, something remarkable has been happening to the structure of the core and the surrounding layers. As each new fuel ignites in the center and eventually runs out, the ash from that fuel doesn't just disappear, it stays. And the next fuel ignites in a shell around the growing ball of ash. The result is that the star develops a layered structure, like an onion with each layer made of a different element. Picture it from the outside inward. The outermost layer is still hydrogen, the original atmosphere of the star, the vast red supergiant envelope that makes Betelgeuse look the way it does. Beneath that is a layer where hydrogen is actively fusing into helium. Below that is a layer of helium. Below that, a shell where helium is fusing into carbon and oxygen. Below that, a layer of carbon and oxygen. Then a shell where carbon is burning. Then a layer of neon and magnesium. Then a shell where neon is burning. Then a layer of oxygen and silicon. Then a shell where oxygen is burning. Then a layer of silicon and sulfur. Then the innermost shell where silicon is burning and producing iron. And at the very center, a growing ball of iron ash, getting heavier and denser with every passing hour. Each of these shells is burning simultaneously. The star is not going through these stages one at a time in a neat sequence anymore. Once a fuel is ignited, it continues to burn in a shell around the core even after the center has moved on to the next fuel. The star has become a nested set of nuclear furnaces, each one burning a different element, each one producing the ash that feeds the next layer inward. It's an extraordinary structure, and it forms only in the final stages of a massive star's life. No other object in the universe has this kind of internal architecture. But despite all this furious activity, despite all these simultaneous nuclear reactions running at billions of degrees, the surface of the star shows almost nothing unusual. This is the part that seems impossible, but is absolutely true. The outer layers of Betelgeuse are so thick, so massive, so opaque, that they completely insulate the surface from whatever is happening in the core. The core could be quietly fusing helium, or it could be in the final hours of silicon burning, with an iron core growing toward critical mass, and the surface would look essentially the same. The photosphere would still glow at roughly the same temperature. The star would still pulsate in its familiar rhythms. The brightness might vary a little, as it always does, but there would be no dramatic change, no visible sign that the end was imminent. Think about what this means. If you were an astronomer living on a planet orbiting a nearby star, watching Betelgeuse through your telescope, you would see a perfectly normal red supergiant. It would look exactly the way it has looked for thousands of years. You might notice it was slightly brighter or dimmer than average, but red supergiants are variable stars. That's what they do. You would have no reason to suspect that deep inside, the core had reached its final stage. You would have no way of knowing that an iron ball was growing at the center, getting heavier by the hour, approaching a threshold beyond which the entire star would be torn apart. The surface would be calm, the sky would be normal, and then, without any warning visible to your telescope, everything would change. The iron core grows. Each second, each minute, each hour, more silicon is converted into iron in the innermost burning shell, and that iron settles onto the core. The core gets heavier. It also gets denser, because the iron is being compressed by the enormous weight of all the material above it. At this point, the core is supported primarily by a quantum mechanical effect called electron degeneracy pressure. This is not the same kind of pressure you experience in everyday life. It's not caused by heat or by particles bouncing around. It's caused by a fundamental law of quantum physics that says no two electrons can occupy the same quantum state in the same place. When matter is compressed to extreme densities, the electrons are forced into higher and higher energy states, simply because the lower states are already occupied. This creates an outward pressure that resists further compression. It's the same force that supports white dwarf stars, the dense remnants of smaller stars that have finished their lives. But electron degeneracy pressure has a limit. In 1930, an Indian physicist named Subramanian Chandrasekhar, then only 19 years old, calculated that electron degeneracy pressure can support a mass of only about 1.4 times the mass of our Sun. If the mass exceeds that threshold, the electrons cannot push back hard enough. Gravity wins. This critical mass is called the Chandrasekhar limit, and it is one of the most important numbers in all of astrophysics. It determines the boundary between a star that can die quietly and one that must die violently. As silicon burning continues in the shell around the iron core, the core creeps closer and closer to this limit. 1.2 solar masses, 1.3, 1.35. The core is getting denser. The electrons are being squeezed into higher and higher energy states. They are pushing back as hard as quantum mechanics allows them to push. But the mass keeps increasing. And here's where something insidious begins to happen. Something that seals the star's fate before the core even reaches the Chandrasekhar limit. The core is so hot, so dense, that highly energetic photons inside it start doing something destructive. They begin smashing iron nuclei apart. This process, called photodisintegration, breaks iron nuclei back down into helium nuclei and free neutrons. This is the reverse of what the star has been doing its entire life. Instead of building heavy elements from light ones and releasing energy, the core is now tearing heavy elements apart and absorbing energy. Each iron nucleus that is shattered steals energy from the core, reducing the thermal pressure that was helping to support it. At the same time, another process is beginning. The electrons, the very particles whose degeneracy pressure is holding the core up, are being captured by protons inside the remaining nuclei. This process, called electron capture, converts protons into neutrons while releasing neutrinos. Every electron that is captured is an electron that is no longer contributing to the degeneracy pressure. The floor is being pulled out from under the core from two directions simultaneously. Photodisintegration is stealing thermal energy. Electron capture is removing degeneracy pressure. The two pillars holding up the core are being knocked away at the same time. The core is trapped. It cannot generate new energy because ion fusion is endothermic. It cannot maintain its temperature because photodisintegration is draining energy away. It cannot maintain electron degeneracy pressure because electrons are being captured faster than they can be replaced. Every process that could support the core is failing simultaneously. There is no escape. There is no new fuel to ignite. There is no new source of pressure to call upon. The star has run out of options, and the surface still looks normal. The photosphere still glows at 3,000 degrees. The star still pulses gently. The familiar reddish light still streams outward into space, traveling at 300,000 kilometers per second, heading toward Earth, carrying an image of a star that appears to be perfectly fine. An astronomer looking at Betelgeuse at this moment would see nothing unusual. The spectrum would look normal. The brightness would be within its typical range. There would be no sign whatsoever that a catastrophe was about to occur. This is the most extraordinary disconnect in all of stellar physics. The surface and the core are experiencing entirely different realities. The surface is living in a calm, stable, ordinary moment. The core is standing at the edge of an abyss, and the surface has no idea. The light travel time from the core to the surface is so long, the material between them so thick and opaque, that the core could completely collapse before the surface felt any effect at all. The outer layers of the star are still responding to conditions that existed in the core days or weeks ago. They are out of date. They are looking at old news, and by the time the new news reaches them, it will be too late. The iron core reaches 1.4 solar masses, the Chandrasekhar limit. Electron degeneracy pressure reaches its maximum and finds that maximum is no longer enough. Photo disintegration and electron capture have weakened the core just enough that gravity finally gains the upper hand. And in that instant, in less than a second, the core begins to collapse. What happens next is one of the most violent and energetic events the universe is capable of producing. The core does not fall slowly. It does not sag or settle or gradually compress. It falls inward at a significant fraction of the speed of light. The iron core, a ball roughly the size of Earth, containing 1.4 times the mass of our Sun, collapses to a ball roughly the size of a city in less than 1 second. The density shoots up to values that are almost beyond comprehension. The temperatures reach tens of billions of degrees. And in that collapsing inferno, a flood of particles is released that will carry more energy in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. Those particles are neutrinos, and they are about to become the most important messengers in the story of Betelgeuse, because they will be the first signal, the ghost signal, the warning that reaches Earth before any visible light. They will tell us that the core has fallen, that the star is dying, and that something spectacular is about to appear in the sky. But on the surface of Betelgeuse, in the moment the core begins its collapse, nothing has changed yet. The red supergiant still glows. The photosphere still radiates its familiar warmth into space. The star still hangs on Orion's shoulder, looking exactly the way it has looked for thousands of years. The light from the surface still has no idea what has just happened deep inside, but it is about to find out. The core falls, not slowly, not gradually, not in any way that human intuition can prepare you for. The inner core of Betelgeuse, a ball of iron roughly the size of Earth, containing approximately 1.4 times the mass of our Sun, collapses inward at speeds approaching 70,000 kilometers per second. That is nearly a quarter of the speed of light. In less than a single second, this ball of matter, which moments ago occupied a volume comparable to our entire planet, crushes itself down to a sphere roughly 12 to 15 miles across, the size of a city. All that mass squeezed into a space so small you could drive across it in 20 minutes. The density inside this collapsing core reaches values that are almost meaningless to describe in everyday terms. A single teaspoon of the material at these densities would weigh roughly 4 billion tons. That is more than the combined mass of every building, every vehicle, every object ever constructed by human civilization. In 1 teaspoon. And this density exists across the entire core. A sphere 12 to 15 miles in diameter, packed with matter so compressed that atomic nuclei are touching, that individual protons and neutrons are pressed together into a continuous fluid of nuclear matter. The core has become something that no longer resembles anything in ordinary experience. It has become something new. But let's slow down and understand what is actually happening inside this collapse, because the physics is extraordinary, and it involves a particle that most people have heard of, but very few truly appreciate. The neutrino. As the core collapses and the density skyrockets, the electrons inside it are being squeezed into tighter and tighter spaces, alongside atomic nuclei. At these extreme densities, the electrons don't just orbit the nuclei or flow between them like they would in normal matter. They are crushed directly into the nuclei themselves. And when an electron is forced into a proton at these energies, a fundamental nuclear reaction occurs. The electron and the proton combine and transform into a neutron and a neutrino. The proton and electron essentially merge, and the neutrino is released as a byproduct. This process, electron capture, is happening everywhere throughout the collapsing core simultaneously. Trillions upon trillions upon trillions of electrons are being captured by protons every fraction of a second. Each capture removes one electron from the core, which means one fewer particle contributing to the electron degeneracy pressure that was trying to hold the core up. And each capture produces one neutrino, which immediately begins traveling outward. The collapse feeds on itself. Every captured electron makes the remaining pressure weaker, which makes the collapse faster, which forces more electrons into protons, which produces more neutrinos, which makes the pressure even weaker. It is a runaway process, a cascade that cannot be stopped once it begins. The number of neutrinos produced during this collapse is beyond staggering. In roughly 10 seconds, the collapsing core releases approximately 10 to the 58th power neutrinos. That is a 1 followed by 58 zeros. These neutrinos carry away roughly 99% of all the energy released during the entire collapse. Let me say that again, because it is one of the most remarkable facts in all of astrophysics. When a massive star's core collapses, the overwhelming majority of the energy does not come out as light. It does not come out as the spectacular visible explosion that we call a supernova. It comes out as neutrinos, invisible, ghostly, nearly undetectable particles that pass through matter as if it were not there. The visible supernova, the brilliant flash of light that will illuminate the sky, represents only about 1% of the total energy released. The other 99% is carried silently away by neutrinos that most of the universe will never notice. The total energy released during the collapse is approximately 3 times 10 to the 46th joules. That is more energy than our sun will produce in its entire 10 billion year lifetime. And nearly all of it is released in about 10 seconds. 10 seconds of neutrino emission carrying more energy than 10 billion years of sunshine. The power output during those 10 seconds is briefly comparable to the combined luminosity of every star in the entire observable universe. This is not an exaggeration. This is the calculated, verified, scientifically established magnitude of what happens when a stellar core collapses. Now, here is what makes neutrinos so remarkable and so important for our story. Neutrinos barely interact with ordinary matter. A neutrino can pass through the entire Earth without touching a single atom. It can pass through a wall of a lead a light year thick and emerge on the other side completely unaffected. Neutrinos are sometimes called ghost particles because they move through the physical world like phantoms, unimpeded by the matter that blocks everything else. Light cannot escape from the core because the core is surrounded by hundreds of solar radii of dense, opaque plasma. Photons are absorbed and re-emitted billions of times on their way outward, taking hours, days, or even weeks to work their way to the surface. But neutrinos are different. Neutrinos pass straight through the star. They stream outward from the collapsing core at very close to the speed of light. And the entire mass of the star, all 15 to 20 solar masses of gas and plasma piled above the core, barely slows them down at all. Within seconds of being produced, the neutrinos are already free of the star and racing outward into space. This creates an extraordinary situation. The neutrinos will reach Earth before the light does, not by a small margin, by hours, possibly by many hours. The reason for this delay is the same reason we discussed earlier. The surface of Betelgeuse does not know what has happened in the core. Information about the collapse has to travel outward through the star, and it does so at a speed limited by the physics of how shock waves move through dense plasma. The collapse happens in the core, a shock wave forms and begins pushing outward, but it takes time for that shock wave to traverse the hundreds of solar radii of material between the core and the surface. Current models estimate that the shock wave needs roughly 1 to several hours to break through the surface of a red supergiant like Betelgeuse. Some models suggest it could take even longer, depending on the exact structure of the star's envelope. But the neutrinos don't wait for the shock wave. They leave immediately. They pass through the entire star in a fraction of a second and head toward Earth at essentially the speed of light. So there will be a window, a gap, between the arrival of the neutrinos and the arrival of the first visible light from the explosion. During that window, the neutrinos will have already reached Earth and been detected by our instruments. But the sky will still show a calm, ordinary Betelgeuse glowing peacefully on Orion's shoulder. The ghost signal will have arrived, and the visible show will not have started yet. We know this is real because it happened before. On February 23rd, 1987, a star exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way about 168,000 light-years away. This supernova, designated SN 1987A, was the closest observed supernova since the invention of the telescope. And roughly 3 hours before the first visible light from the explosion was detected by astronomers, 2 neutrino detectors on Earth registered a burst of neutrinos. The Kami-Okande 2 detector in Japan recorded 11 neutrinos. The IMB detector in Ohio recorded 8. A total of about 24 neutrinos were detected across several experiments around the world. 24 particles out of the roughly 10 to the 58th power that were emitted. That's how weakly neutrinos interact with matter. An almost incomprehensible flood of neutrinos washed through the Earth, and our detectors caught barely 2 dozen. But those 2 dozen were enough to confirm that the theoretical models were correct. Neutrinos really do arrive before the light. The ghost signal is real. Now, SN 1987A was 168,000 light-years away. Betelgeuse is only roughly 550 to 700 light-years away. That is roughly 240 to 300 times closer. The number of neutrinos that would pass through our detectors from a Betelgeuse supernova would be enormously greater than what we saw from SN 1987A. Modern neutrino detectors are also far more sensitive than the ones that existed in 1987. Super Kami-Okande in Japan, the successor to the original Kami-Okande detector, contains 50,000 tons of ultra-pure water surrounded by thousands of sensitive light sensors. Ice Cube, a detector buried in the Antarctic ice sheet. Instruments, a cubic kilometer of ice. Other detectors around the world, including planned next-generation facilities like Hyper Kami-Okande and Dune, would add even more capability. If Betelgeuse's core collapsed today, these detectors would not register a handful of neutrinos. They would register thousands, possibly tens of thousands. The signal would be unmistakable. Every neutrino observatory on the planet would light up simultaneously, with a burst of detections all arriving within a span of about 10 seconds. Scientists would know immediately what had happened. A core collapse, a nearby star dying, and they would know which direction the neutrinos came from, narrowing it down to a region of sky that includes Betelgeuse. There is already a system in place for exactly this scenario. It is called the Supernova Early Warning System, or SNOOS. This is a network linking neutrino detectors around the world. If multiple detectors register a simultaneous burst of neutrinos consistent with a core collapse, SNOOS automatically sends an alert to astronomers worldwide. The alert would go out within minutes. Astronomers would immediately point every available telescope at Betelgeuse, waiting for the light to arrive. For the first time in history, humanity would be watching a star, knowing that it had already died, waiting for the visible evidence to reach us. We would be staring at a star that, at that very moment, was being torn apart from the inside, but whose surface still appeared normal because the shock wave hadn't broken through yet. The hours between the neutrino detection and the first visible light would be among the most extraordinary hours in the history of science. Every major observatory would be mobilized. Every space telescope would be redirected. Billions of people would be told that something was about to happen, that one of the brightest stars in the sky was about to explode, and they should go outside and look up. Think about what that experience would feel like. You step outside on a clear night and you find Orion in the sky. You look at Betelgeuse and you see exactly what you have always seen. A reddish star, steady and calm, glowing the way it has glowed for your entire life. Nothing about it looks wrong. Nothing about it looks different. It is just a star. But you know because scientists have told you, because the news has told you, because the alert has gone out to every corner of the globe. That star is already dead. Its core has already collapsed. A shockwave is already tearing through its interior. And in a matter of hours, maybe sooner, the light from that catastrophe will reach this planet, and the calm star you are looking at will be replaced by something brighter than the moon. You are watching a ghost, an image painted by ancient light that left the star's surface before the core fell. And soon, very soon, the new light will arrive and the ghost will vanish, and something extraordinary will take its place. You would be standing on your front lawn, or on a rooftop, or in a field, staring up at a star that no longer exists, waiting for the universe to deliver the news. There is nothing in human experience quite like that. We have never before known that a star was dying in real time. We have never before had the chance to watch and wait for an explosion we knew was coming. This would be the first time, and the anticipation, the sheer electric tension of those hours, would be felt by every human being on Earth who looked up at the sky and understood what they were seeing. And then, it would begin. Let me describe what happens inside the star during those hours, because the journey from core collapse to visible explosion is not straightforward. The collapse of the iron core does not immediately blow the star apart. In fact, the initial collapse almost fails to produce an explosion at all. This is one of the great puzzles of supernova physics, and it took decades of research and some of the most complex computer simulations ever run to begin to understand it. When the inner core collapses to nuclear density, to the point where neutrons are packed as tightly as they are inside an atomic nucleus, a new form of pressure kicks in. The strong nuclear force, the force that holds protons and neutrons together inside nuclei, becomes repulsive at very short distances. When the core is compressed beyond nuclear density, this repulsive force pushes back. Hard. The collapse doesn't just stop, it bounces. The inner core rebounds like a compressed spring suddenly released, sending a shockwave outward into the still infalling material above it. This bounce happens in a fraction of a millisecond. The shockwave that forms is enormously powerful. For a brief instant, it contains more than enough energy to blow the entire star apart. If this shockwave could simply plow outward through the rest of the star without losing energy, the star would explode immediately. But it can't. As the shockwave pushes outward into the still falling outer core, it encounters a wall of iron and silicon, still raining down at tens of thousands of kilometers per second. The shock has to push against this infalling material, and that costs energy. Even worse, as the shock moves outward through the iron layer, it heats the iron to such extreme temperatures that the iron nuclei begin to break apart. Photodisintegration again. Each iron nucleus that the shock shatters absorbs energy from the shockwave. The shock is spending its energy breaking apart iron, and this drain is enormous. Within milliseconds, the shockwave stalls. It stops moving outward. It just sits there, a hot, dense shell of material suspended somewhere inside the core, unable to advance, unable to retreat. The star, at this moment, is not exploding. The shock has failed. If nothing intervenes, the shock will simply dissipate. The rest of the star will fall inward onto the core, and the entire star will collapse into a black hole without ever producing a visible supernova. But something does intervene. The neutrinos. Remember those 10 to the 58th neutrinos streaming outward from the newly formed proto-neutron star at the center? I said earlier that neutrinos pass through ordinary matter almost without interaction, and that's true. Almost. But the material just behind the stalled shockwave is not ordinary matter. It is matter at densities and temperatures so extreme that even neutrinos, those ghostly particles that can pass through light years of lead, begin to interact with it in meaningful numbers. Not most of the neutrinos, not even a large fraction, but a tiny percentage of that titanic flood of neutrinos is absorbed by the material behind the stalled shockwave. And even a tiny percentage of a number as large as 10 to the 58th is still an enormous amount of energy. This energy deposition heats the material behind the shock. It increases the pressure, and over the course of roughly 100 to several hundred milliseconds, an eternity in the context of a process that has been happening in fractions of seconds, the neutrino heating builds up enough pressure to revive the shockwave. The shock begins to move outward again, slowly at first, then faster as it gains momentum, and as the density of the infalling material above it decreases. This is called the delayed neutrino-driven mechanism, and it is the leading theory for how most core collapse supernovae actually explode. The initial bounce provides the shock, but it's the neutrinos that ultimately power the explosion. The ghost particles, the ones that carry away 99% of the energy and barely interact with anything, end up being the very thing that makes the supernova visible. Without them, the shock would fail, and the star would collapse silently into a black hole. With them, just barely, just by the thinnest margin, the shock is revived, and the star is torn apart. The revived shockwave now begins its journey outward through the star. It plows through the successive layers of the onion structure, the shells of silicon, oxygen, neon, carbon, helium, and hydrogen that we described earlier. As it passes through each layer, it heats the material to enormous temperatures, triggering explosive nuclear burning. Elements are forged in the shockwave that could never be created under normal conditions. Some of these elements are heavier than iron, built by the flood of free neutrons released during the collapse in a process called rapid neutron capture. Gold, platinum, uranium, many of the heaviest elements on the periodic table are forged in these final moments. They're created in the shock wave and blasted outward along with everything else. The shock wave accelerates as it moves outward through the star. The density of the material drops as you move away from the core, so the shock has less resistance to push against. By the time it reaches the hydrogen envelope, the outermost layers of the star, it is moving at thousands of kilometers per second. And then it breaks through the surface. This is the moment. The moment the shock wave erupts from the photosphere of Betelgeuse. The moment the star, which has appeared calm and ordinary for all the hours since the core collapsed, suddenly and violently reveals what has happened inside it. The surface temperature, which had been a cool 3,000 or so degrees, skyrockets as the shockwave arrives. The luminosity jumps by a factor of millions in a matter of minutes. A wave of ultraviolet light and X-rays is released as the superheated shock-heated gas is exposed to space. This initial flash is called the shock breakout, and it lasts only minutes to perhaps an hour, but it is extraordinarily bright. From Earth, the effect would be immediate and unmistakable. A new light would appear in the sky where Betelgeuse had always been, but vastly, overwhelmingly brighter. How bright exactly is difficult to predict with certainty, because it depends on the details of the explosion, the mass of the envelope, the energy of the shockwave, and the viewing angle. But current models and historical comparisons suggest that at its peak, a Betelgeuse supernova could reach an apparent magnitude somewhere in the range of roughly -11 to -13. To put that in perspective, the full moon has an apparent magnitude of about -12.7. So a Betelgeuse supernova could rival the full moon in brightness. Some models suggest it could be slightly dimmer than the full moon. Others suggest it could be comparable or even briefly brighter. The uncertainty is real, but the range is clear. We are talking about something vastly brighter than any star or planet in the sky. Bright enough to cast shadows on the ground at night. Bright enough to be clearly visible during broad daylight. Imagine walking outside on a clear afternoon and looking up to see a blazing point of light in the sky near where Orion should be. Not the sun, not the moon, but a star. A single star, shining with the intensity of the full moon or close to it, visible against the blue of the daytime sky. This would not be a subtle phenomenon. This would be a spectacle visible to every human being on the side of Earth, facing that part of the sky. No telescope needed, no special equipment. Just walk outside and look up. A new light in the heavens, brighter than anything anyone alive has ever seen in the night sky. This peak brightness would not last forever. The supernova would remain extraordinarily bright for several weeks, then gradually fade over the course of months. For those first few weeks, night would not be truly dark in any part of the world where the supernova was above the horizon. There would be a second moon in the sky, casting a faint but visible light across the landscape. Over the following months, the supernova would fade from naked eye brilliance to something dimmer, though it would likely remain visible without a telescope for a year or more. Eventually, over years, the expanding cloud of debris would dim to the point where only telescopes could see it. But for that initial period, for those first weeks and months, the sky would be transformed. Now, a natural question arises. Should we be worried? If a star 550 to 700 light years away explodes with this kind of violence, would it be dangerous to life on Earth? The short answer is no. Betelgeuse is far enough away that the supernova would be spectacular, but not threatening. Let me explain why. The primary dangers from a nearby supernova are high-energy radiation, specifically gamma rays and X-rays, and energetic particles known as cosmic rays. A supernova does produce enormous amounts of both. The initial shock breakout releases a burst of X-rays and ultraviolet radiation. Gamma rays can be produced by the decay of radioactive elements forged in the explosion, and the expanding shock wave accelerates particles to near light speed, producing cosmic rays that can travel across interstellar distances. But intensity drops with distance, and it drops steeply. Radiation follows the inverse square law, meaning that if you double the distance, the intensity drops to 1/4. If you increase the distance by a factor of 10, the intensity drops by a factor of 100. Betelgeuse is 550 to 700 light years away. At this distance, the radiation reaching Earth from the supernova would be minuscule compared to what we receive from our own sun every day. The X-rays and ultraviolet light from the shock breakout would be absorbed by Earth's atmosphere long before reaching the ground. The gamma rays would be far too weak at this distance to significantly affect the ozone layer, which is the primary mechanism by which a nearby supernova could harm life. Studies have estimated that a supernova would need to be within roughly 25 to 50 light years of Earth to pose a genuine threat to the biosphere. Betelgeuse is more than 10 times farther than that danger threshold. The cosmic rays from the explosion would also be greatly diluted by the time they reached Earth, spread out over an enormous volume of space, and cosmic rays don't travel in straight lines. They are deflected by magnetic fields in interstellar space, so they would arrive gradually over thousands of years, rather than all at once. The increase in cosmic ray flux at Earth from a Betelgeuse supernova would be negligible compared to the background cosmic radiation we already receive from other sources. So, the event would be safe. Entirely safe. There is no credible scientific scenario in which a Betelgeuse supernova harms life on Earth. What it would be is beautiful, dramatic, and scientifically priceless. Think about what astronomers would learn. A core collapse supernova at 550 to 700 light years would be the closest such event observed with modern instruments by an enormous margin. SN 1987A, the only supernova for which neutrinos were detected, was 168,000 light years away. Betelgeuse is hundreds of times closer. The neutrino signal would contain tens of thousands of detections rather than 24, allowing scientists to measure the energy, timing, and flavor composition of the neutrino burst with extraordinary precision. This data would test our models of core collapse, neutron star formation, and neutrino physics in ways that no laboratory experiment can. It would be the single most important dataset in the history of stellar physics. Every telescope on Earth and in orbit would observe the event continuously. The light curve, the way the brightness changes over time, would be measured with exquisite accuracy across every wavelength from radio waves through infrared, visible light, ultraviolet, X-rays, and gamma rays. Gravitational wave detectors might register a signal from the asymmetric collapse of the core, another first that would test general relativity under extreme conditions. For the general public, the supernova would be an event unlike anything in living memory. The last supernova visible to the naked eye in our own galaxy was observed in 1604, over 400 years ago. That event, known as Kepler's supernova, was seen by astronomers including Johannes Kepler himself, but it occurred before the invention of modern telescopes. Before that, a supernova was observed in 1054 by Chinese and possibly Arab astronomers. That explosion created the Crab Nebula, which we can still see today as a glowing cloud of gas nearly 1,000 years later. A Betelgeuse supernova would be the first naked-eye supernova in our galaxy in over 4 centuries. It would be one of the defining astronomical events of human history. Billions of people would see it. It would be photographed, filmed, live-streamed, discussed, debated, and remembered for generations. Children alive when it happens would tell their grandchildren about the night a star on Orion's shoulder blazed brighter than the moon. And through it all, buried inside the expanding cloud of debris, something would remain. Something small, dense, and extraordinary. The remnant of the core that started this entire chain of events. Whether that remnant is a neutron star or a black hole is one of the most important unanswered questions about Betelgeuse, and it depends on details we cannot yet determine with certainty. But before we can discuss what that remnant might be, we need to follow the expanding shockwave outward, past the surface of the star, into the surrounding space where Betelgeuse has been shedding material for thousands of years. Because the explosion does not happen in empty space, it happens in an environment shaped by the star's own history. And the collision between the supernova shockwave and that surrounding material will create structures that persist for thousands of years. Visible reminders of the night a familiar star died and became something entirely new. The shockwave breaks through the surface of Betelgeuse and erupts into space, carrying with it the shattered remains of a star that burned for roughly 8 to 10 million years. Material that once formed the outer layers of one of the largest stars visible from Earth is now flying outward at thousands of kilometers per second. A wall of superheated gas expanding in every direction like an unimaginably violent balloon. But this expanding debris does not fly outward into emptiness. It flies into a region that Betelgeuse has been sculpting for millennia. Red supergiants are messy stars. They do not hold onto their outer layers the way smaller, more compact stars do. Throughout its life as a red supergiant, Betelgeuse has been steadily shedding material from its surface through powerful stellar winds. These winds are driven by a combination of radiation pressure from the star's enormous luminosity and by the pulsations that cause the outer layers to expand and contract rhythmically. Every time the surface expands outward during a pulsation cycle, some of the outermost gas gains enough momentum to escape the star's gravitational pull entirely. This material drifts away into space, cooling as it goes, forming dust grains and gradually building up a complex structure around the star. Over the tens of thousands of years that Betelgeuse has been a red supergiant, this process has deposited an enormous amount of material into the surrounding space. Observations from infrared telescopes and submillimeter observatories have revealed that Betelgeuse is surrounded by multiple shells and arcs of gas and dust, extending outward for several light years. Some of this material forms relatively smooth shells, the remnants of long, steady periods of mass loss. Other structures are clumpy and asymmetric, reflecting episodes where the wind was stronger on one side of the star than the other, or where large convective cells on the surface ejected material in preferred directions. The Great Dimming of 2019 to 2020 was caused by exactly this kind of localized ejection. And that event deposited material relatively close to the star. Further out, there are older, larger structures created by similar events over thousands of years. When the supernova shockwave slams into this circumstellar material, something spectacular happens. The shockwave, moving at several thousand to tens of thousands of kilometers per second, collides with gas and dust that is essentially standing still. The collision heats the circumstellar material to millions of degrees. It compresses it, lights it up, and makes it glow across the electromagnetic spectrum, from radio waves through infrared and visible light, all the way to X-rays. The expanding shockwave becomes visible not just through its own emission, but through its interaction with the environment the star spent millennia creating. It is as if the dying star lit a fuse in a landscape it built itself, and now the landscape is catching fire. This interaction between the supernova ejector and the circumstellar material is not a brief event. It unfolds over years, decades, and centuries. As the shock wave expands and encounters different shells and structures at different distances from the star, new regions light up. The supernova remnant grows and evolves, changing shape and brightness over time. From Earth, astronomers would watch this process unfold in real time, using telescopes to track the expanding shock as it illuminates successive layers of Betelgeuse's ancient wind. We have examples of exactly this kind of interaction in other supernova remnants. SN 1987A, the supernova in the Large Magellanic Cloud, has been interacting with circumstellar material for decades. Images from the Hubble Space Telescope show a glowing ring of gas around the supernova, material that the star shed thousands of years before the explosion, now lit up by the shockwave slamming into it. The ring has grown brighter and more complex over the years, as the shock catches up with more and more of the pre-existing material. A Betelgeuse supernova would produce similar structures, but being so much closer, the detail visible in our telescopes would be extraordinary. We would watch the formation of a supernova remnant in unprecedented resolution, tracking individual clumps and filaments of gas as they were heated and compressed by the expanding shock. Over longer timescales, over hundreds and thousands of years, the expanding material would form a full supernova remnant. The Crab Nebula, one of the most famous objects in the sky, is a supernova remnant created by an explosion observed in 1054, nearly 1,000 years ago. Today it spans about 11 light years across, a glowing cloud of gas and energetic particles still powered by a rapidly spinning neutron star at its center. The Velar supernova remnant, created by an explosion roughly 11,000 years ago, now spans about 100 light years. Cassiopeia A, the remnant of an explosion roughly 340 years ago, is about 10 light years across and still expanding. A Betelgeuse supernova remnant would follow a similar trajectory. In the first years and decades, the expanding debris would be relatively compact, a small but brilliantly glowing cloud visible through telescopes. Over centuries, it would grow, sweeping up surrounding interstellar gas and dust, forming the intricate filamentary structures we see in older remnants. Over thousands of years, it would expand to span light years, eventually becoming a vast, diffuse nebula visible from Earth as a faint glowing patch in the region where Betelgeuse once stood. Now, let's talk about what this means for the night sky. Because the explosion of Betelgeuse would permanently alter one of the most recognizable features of the heavens. Orion is arguably the most widely known constellation. Its pattern of bright stars is visible from nearly every inhabited location on Earth. The 3 belt stars, the 2 shoulder stars, the 2 knee stars, the sword hanging from the belt. This arrangement has been identified and named by cultures spanning every continent and every era of human history. Betelgeuse marks Orion's left shoulder, and it is one of the 2 brightest stars in the constellation, the other being Rigel at the right knee. When Betelgeuse explodes, that familiar pattern will be broken. The left shoulder of Orion will be replaced first by a blazing point of light, far brighter than anything else in the sky. And then, as weeks and months pass, by a fading glow. Over the course of a year or 2, the supernova would dim from its spectacular peak to a level comparable to ordinary bright stars, then continue fading. Within a few years, it would no longer be visible to the naked eye. The point of light that had marked Orion's shoulder for all of recorded human history would be gone. In its place, telescopes would show an expanding cloud of gas, growing slowly larger and more complex over the decades. To the naked eye, the shoulder of Orion would simply be empty. The constellation would look lopsided, incomplete, missing a piece that generations of stargazers had taken for granted. New generations would grow up knowing Orion as a pattern with a gap where the left shoulder used to be. They might not even miss it. For them, a 6-star Orion would be the only Orion they had ever known. But for anyone who saw the constellation before the explosion, the absence would be striking and permanent. Eventually, thousands of years in the future, the supernova remnant might grow large enough to be faintly visible to the naked eye as a diffuse patch of light, a nebula occupying the space where a star once shone. Orion would have a new feature, not a bright point of light, but a soft cloud, the expanding remains of a dead star slowly dispersing into the surrounding galaxy. The constellation would tell a new story, not of a mighty hunter, but of the place where one of the sky's most famous stars died and left its mark on the cosmos. Let me now turn to the question that sits at the very center of this story, quite literally. What is left behind inside the expanding debris? What happened to the core? When the shock wave was revived and the outer layers of the star were blown apart, the core itself remained. The innermost region, the part that collapsed to nuclear density and bounced to form the shockwave, is still there. It did not explode. It did not fly apart. It stayed, compressed to extraordinary density, a ball of matter roughly 12 to 15 miles across, containing roughly 1.4 to 2 solar masses of material. In the moments after the shockwave left, this proto-neutron star was incredibly hot, with temperatures exceeding 100 billion degrees, and it was radiating energy furiously through neutrino emission. Over the following minutes and hours, it cooled rapidly, settling into a more stable configuration. Whether this object becomes a neutron star or collapses further into a black hole depends on one critical question: how much mass does it retain? If the mass of the remnant stays below a threshold known as the Tolman-Oppenheimer-Volkoff limit, which is estimated to be somewhere around 2 to 2.2 solar masses, depending on the still uncertain properties of matter at nuclear density, then neutron degeneracy pressure and the repulsive component of the strong nuclear force can hold the remnant up against gravity. The result is a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons, spinning rapidly, possibly many times per second, and possessing a magnetic field trillions of times stronger than Earth's. If the remnant is a neutron star, it would be an extraordinary object. Consider what happens to the spin. Betelgeuse, like all stars, rotates. It rotates slowly because it is enormous, the way a figure skater spins slowly with arms extended. But when the core collapses from the size of Earth to the size of a city, the same physical principle that makes a skater spin faster when they pull their arms in takes over. Conservation of angular momentum. The rotation that was spread across a planet-sized core is now concentrated into a sphere 12 to 15 miles across. The result is a newborn neutron star spinning at extraordinary speed, potentially dozens of times per second. Some neutron stars, called millisecond pulsars, spin hundreds of times per second. The surface of such an object would be moving at a significant fraction of the speed of light, completing a full rotation faster than you can blink. The magnetic field is equally extreme. Earth has a magnetic field strong enough to deflect a compass needle. The Sun's magnetic field is a few times stronger. A neutron star's magnetic field can be trillions of times stronger than Earth's, and in the most extreme cases, a type of neutron star called a magnetar. The field reaches 1,000 trillion times Earth's field strength. Magnetic fields this intense can distort the shapes of atoms and alter the fundamental behavior of matter in their vicinity. A magnetar's field carries more energy per cubic centimeter than any other known phenomenon in the universe, except for the interiors of collapsing cores and the immediate neighborhoods of black holes. If a Betelgeuse neutron star were born as a magnetar, it would be one of the most powerful magnetic objects within hundreds of light years of Earth. This rapidly spinning, intensely magnetized neutron star would likely be a pulsar, emitting beams of electromagnetic radiation from its magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If one of the beams happens to point toward Earth, we would detect regular pulses of radio waves, X-rays or gamma rays, each pulse arriving with clockwork precision as the beam sweeps past our line of sight. The Crab Nebula contains exactly such an object, a pulsar spinning roughly 30 times per second that was created in the same explosion that produced the nebula in 1054. A Betelgeuse pulsar, being only 550 to 700 light years away compared to the Crab pulsar's roughly 6,500 light years, would be one of the closest known pulsars to Earth. It would become one of the most intensely studied objects in the sky, a laboratory for testing the physics of matter under conditions that can never be reproduced on Earth. If, however, additional material falls back onto the proto-neutron star after the explosion, pushing its mass above the Tolman-Oppenheimer-Volkoff limit, then no known force can resist the collapse. Gravity wins completely. The remnant collapses through its own event horizon and becomes a black hole, a region of space where the curvature of space-time is so extreme that nothing, not even light, can escape. For Betelgeuse, the answer is genuinely uncertain. The mass of the remnant depends on how much of the star's core is ejected by the explosion and how much falls back. This in turn depends on the energy of the explosion, the structure of the star at the moment of collapse, the degree of asymmetry in the shock wave, and other details that cannot be predicted precisely with current models. Betelgeuse's estimated mass of 15 to 20 solar masses places it in a range where both outcomes are plausible. Stars at the lower end of this range tend to produce neutron stars. Stars at the higher end are more likely to produce black holes. But the boundary is not sharp, and individual cases can go either way depending on the specifics. If the remnant is a black hole, it would be a stellar mass black hole, far smaller than the supermassive black holes that sit at the centers of galaxies like the one at the center of the Milky Way, Sagittarius I star, which has 4 million solar masses. A Betelgeuse black hole would have only a few solar masses. Its event horizon would be only a few miles across. It would be invisible in visible light, detectable only by its gravitational effects on surrounding matter, or by the radiation emitted by material falling into it. At Betelgeuse's distance from Earth, detecting a quiet stellar mass black hole with no infalling material would be extremely difficult. We might know it was there because of the absence of a pulsar signal and the presence of a compact X-ray source, but confirming its nature would require careful, long-term observation. The honest answer, the scientifically responsible answer, is that we do not know which outcome to expect. Both are possible. Both are consistent with what we know about Betelgeuse's mass and the physics of core collapse. When the supernova eventually happens, the neutrino signal might help distinguish between the two scenarios. If the neutrino burst cuts off abruptly after a few seconds, it could indicate that the proto-neutron star collapsed into a black hole, swallowing its own neutrino-emitting surface. If the neutrino emission tapers off gradually over tens of seconds, it would suggest that a stable neutron star formed. This difference in the neutrino signal could tell us what the remnant is, even before the light from the explosion reaches Earth. Let's step back from the remnant now and think about something else that the explosion would scatter into space, because the supernova does not just produce a compact remnant and a pretty nebula, it produces something far more important for the long-term story of the universe. It produces elements. Throughout its life, Betelgeuse built increasingly heavy elements in its core. Hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, neon into oxygen and magnesium, oxygen into silicon and sulfur, silicon into iron. These elements were trapped inside the star, layered in the onion shell structure of the core, inaccessible to the rest of the universe. But the supernova changes that. The explosion rips the star apart and scatters all of these elements into interstellar space. Carbon, oxygen, silicon, iron, every element that the star spent millions of years carefully building is released in a single violent event, sprayed outward at thousands of kilometers per second. But the explosion does more than just release pre-existing elements. It creates new ones. During the passage of the shock wave through the outer layers of the star, the extreme temperatures and densities trigger explosive nucleosynthesis, fusion reactions that create elements heavier than iron. Under normal stellar conditions, building elements heavier than iron requires energy input rather than releasing it, which is why normal fusion stops at iron. But in the seconds during which the shock wave passes through the star, the conditions are so extreme that a different process takes over. A flood of free neutrons, released during the collapse and the subsequent nuclear reactions, is captured by existing nuclei in rapid succession. This process, known as rapid neutron capture or the R process, builds nuclei far heavier than iron by adding neutron after neutron faster than the nuclei can decay. The result is the creation of elements like gold, platinum, silver, uranium, thorium, and dozens of other heavy elements that cannot be produced by any process inside a living star. Think about what this means. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that fuels nuclear reactors, all of these elements were forged in the death throes of massive stars. They were created in the seconds during which a supernova shockwave tore through a star's outer layers, built by the rapid capture of neutrons under conditions so extreme they exist nowhere else in the universe. Every atom of gold on Earth was once inside a star that exploded. Every atom of silver was scattered across space by a supernova and eventually incorporated into the cloud of gas and dust that collapsed to form our solar system 4.6 billion years ago. When Betelgeuse explodes, it will add its contribution to the galaxy's supply of these heavy elements. The material it scatters will drift through space for millions of years, mixing with the interstellar medium, blending with gas and dust from other sources. Eventually, some of that material will be swept up by the gravity of a collapsing cloud of gas. A new star will form. Planets will coalesce from the leftover debris. And some of the atoms forged in Betelgeuse's death will end up in those planets, in their oceans, in their rocks, and possibly in living things. This is the great cycle of stellar evolution. Stars form from clouds of gas enriched by previous generations of stars. They burn their fuel, build heavy elements in their cores, and eventually die, scattering those elements back into space. The next generation of stars forms from the enriched material, starts with a richer palette of elements, builds new planets, and possibly new life. Every generation adds to the complexity of the universe. Every supernova is both a death and a beginning, an end and a seed. Our own solar system is a product of this cycle. The Sun is not a first-generation star. It formed from material that had already been enriched by multiple generations of stellar evolution and supernova explosions. The iron in Earth's core, the calcium in your bones, the oxygen you're breathing right now, all of it was forged inside stars that died before the Sun was born. You are made of the recycled debris of ancient supernovae. When Betelgeuse explodes, it will be contributing to the raw material of future solar systems, future planets, and potentially future life. Now, let me bring this entire story to a close. Because we started with a simple image, a reddish star on Orion's shoulder, and we've traveled deep inside it, watching its core race through increasingly desperate stages of fusion, watching the iron core grow toward its breaking point, watching the collapse happen in less than a second, watching the neutrinos flood outward as a ghost signal, watching the shockwave stall and revive and finally tear the star apart, watching the explosion light up the sky brighter than the full moon, watching the expanding debris slam into material the star shed over millennia, and watching what remains behind, either a neutron star or a black hole, sitting quietly at the center of a growing nebula. The full picture is this. Betelgeuse is a star in the final phase of its life. It has exhausted the easy fuels and is working through progressively heavier elements at an accelerating pace. At some point, whether thousands of years from now or sooner, its core will build an iron ball that exceeds the Chandrasekhar limit. The core will collapse in under a second. A flood of neutrinos will race outward, reaching Earth hours before any visible light. The shock wave will struggle, stall, and be revived by neutrino heating. The outer layers of the star will be blown into space at thousands of kilometers per second. A supernova will appear in the sky, potentially as bright as the full moon, visible in daylight, casting shadows at night. It will fade over months and years, leaving behind an expanding remnant and a compact object, a neutron star or black hole at the center. The event will be safe. Earth is far enough from Betelgeuse that the radiation and particles from the explosion will be harmlessly diluted by distance. What we will experience is not danger, but wonder. The most spectacular astronomical event visible to the naked eye in over 4 centuries. A moment when billions of people look up and see the sky changed, see a star they recognized reborn as something new and blinding, and understand in a visceral, immediate way that the universe is not static. Stars are born and stars die. The sky we take for granted is a snapshot, a single frame in a movie that has been running for 13.8 billion years. We cannot predict when it will happen. We cannot see the core. We cannot determine whether Betelgeuse has 100,000 years left or is in its final hours. The Great Dimming was not a warning. It was a surface event unrelated to the core's condition. The next real warning will be the neutrinos, and by the time they arrive, the core will have already fallen. There will be no weeks of preparation. There will be no gradual build-up. One day, neutrino detectors around the world will light up simultaneously, and astronomers will know that the countdown to a visible supernova has begun. Hours later, the sky will change. Until that day, Betelgeuse hangs on Orion's shoulder as it has for all of human history. A reddish, slightly variable, seemingly permanent fixture of the winter sky. Cultures have named it and told stories about it for thousands of years. It has guided travelers and inspired poets and puzzled astronomers who noticed its changing brightness and wondered what kind of star could behave that way. It feels permanent because human lifetimes are short and the sky seems eternal. But the sky is not eternal. It only looks that way because we don't live long enough to see it change. Betelgeuse will change. It must. The physics allows no other outcome. Somewhere inside that vast, cool, reddish star, a core is evolving, burning fuel at an accelerating rate, building elements that carry it one step closer to the edge. One day, the iron core will reach its limit. The electrons will be captured. The neutrinos will pour outward. The core will collapse. The shock will revive. And the star will tear itself apart. What was one of the brightest and most beloved stars in the sky will become a supernova, then a fading remnant, then a quiet nebula surrounding a compact object smaller than a city. One familiar star will become something entirely new. A glowing cloud of enriched gas expanding into the galaxy, carrying the elements of future stars and planets and possibly future life. And at its center, a neutron star or black hole, a monument to the power of gravity and the limits of matter, sitting silently in the place where Betelgeuse once shone. The next time you look up at Orion on a clear winter night, find that reddish star on the left shoulder. It looks calm. It looks permanent. It looks like it will be there forever. But now you know what is hiding beneath that surface. Now you know about the onion layers and the iron core and the neutrinos and the shock wave and the ghost signal. Now you know that what you are seeing is not necessarily what is happening right now, but what was happening centuries ago, frozen in light, that has been traveling toward your eyes since before Columbus crossed the Atlantic. Look at that star and understand that you are seeing one of the most dramatic objects in the sky. A giant approaching its end. A clock whose alarm will produce one of the most violent events in the known universe. A star that will one day reshape the familiar sky and remind every human being alive that the cosmos is not a painting. It's a living, evolving, sometimes violent place where stars are born in clouds of gas and die in explosions that briefly outshine entire galaxies. Betelgeuse will explode. The physics is certain. The timing is not. And when it happens, whether we are here to see it, or whether it is our distant descendants who witness the spectacle, it will be a reminder of something profound. The universe recycles everything. The atoms in your body were once inside a star. The iron in your blood was forged in a core, much like Betelgeuse's. The gold in your jewelry was created in the shock wave of an ancient supernova. You are the product of stars that died so that you could live. And one day, Betelgeuse will make its own contribution to that cycle. Its atoms will scatter across space, drift for millions of years, and eventually find their way into new stars, new worlds, and perhaps new beings who will look up at their own sky and wonder about their own place in the universe. That is the story of Betelgeuse, a star that is dying, a star that is beautiful, and a star that, when it finally collapses, will give back everything it ever took from the cosmos, scattered across the galaxy in a single, brilliant, unforgettable moment.